Scientists find sugar in asteroid samples. Searching for an atmosphere at TRAPPIST-1e. China's space science missions for the next 5 years. And NASA loses contact with MAVEN. All this and more in this week's Space Bites. It's been over 2 years since scientists got their hands on Asteroid Bennu, returned from NASA's OSIRIS-REx mission. Side note, I watched that rocket launch. Anyway, and there was a sort of an amazing story about how they got the samples back down to Earth and that they were having trouble actually opening up the sample capsule. But once they actually opened up the sample capsule and started to distribute the samples around to different scientific labs around the world, the scientific discoveries started to pour in. And it was great because actually 2 different asteroids were being studied at the same time. You had OSIRIS-REx and asteroid Bennu, and then you had Hayabusa 2, and asteroid Ryugu. And so you got this comparison between these 2 different asteroids, and they were different in many ways. But one of the sort of stories that has been growing over time is how much of the raw materials of life were present out there in the universe before the Earth formed. And of course, Bennu is an asteroid that's been floating around in the solar system right since the formation of the solar system. And it has a surprising amount of the kinds of molecules that were needed for life in it. There's 3 main categories of molecules that form the precursors for life. The first is nucleobases, and these form DNA, which is the molecule that sort of encodes our recipe for life. And these had been found in asteroid Bennu and in other places in space. And then the second major pillar is amino acids. And of course, these are the building blocks of the proteins that make up our bodies. There are 20 that make up life, and then there are dozens and dozens more. And these various amino acids have been found both in samples of asteroid Bennu and Ryugu, and they've even been found in giant clouds of protostellar material. But the third piece is sugar. And I'm not talking about sucrose or fructose. I'm talking about very simple type of sugar called ribose. And this is one of the building blocks of RNA. And RNA is sort of like a partner to DNA. And one of the long-standing questions is, did life on Earth form? Did you get DNA first, which is a more complicated molecule, or did you start with RNA? So in the samples from asteroid Bennu, scientists detected the presence of ribose, which is this molecule that forms the backbone of RNA. And what's interesting is that another sugar molecule they were looking for was called deoxyribose. And this is like a building block for DNA. They found the ribose, they didn't find the deoxyribose. This is starting to add more credibility to this idea that life started from RNA and not DNA, because you're finding these building blocks in asteroid samples that potentially were raining down on Earth. And then there's another paper where scientists report that they found polymers in samples from asteroid Bennu. So it's a very big week for news about asteroid Bennu. And we've got a bunch of stories on Universe Today this week about this. Pretty big findings. The hunt continues for atmospheres on planets orbiting around red dwarf stars. And these are the only kinds of planets really that can be directly observed right now with telescopes like James Webb. And so even though there have been planets which are Earth-sized, and they're within the habitable zone orbiting around these red dwarf stars, we don't know if they have atmosphere. On the one hand, they're about the size of the Earth. They could have plate tectonics. They could have magnetospheres. They could support an atmosphere for long periods of time. On the other hand, these planets are very close to red dwarf stars, which are known to be very active. They're fully convective. They give off very powerful solar flares. And it's thought that because the planets, in the habitable zone have to be very close to these stars, they would be getting blasted by constant radiation that would evaporate their atmospheres. And so it's believed, well, maybe there's just no atmospheres on these planets. And so there's no real hope to find life on these worlds. But until we either detect or make sure that we haven't detected atmospheres, the search continues. The best place to look, of course, is the TRAPPIST-1 system, where you've got 7 planets, roughly Earth-sized, orbiting around a red dwarf star. Several of them are within the habitable zone. And astronomers have been using James Webb to go planet by planet, looking for any evidence of an atmosphere on one of these worlds. And we've B, no atmosphere, C, no atmosphere, D, probably no atmosphere. And so now we're up to E. I'll give you the spoiler, it's inconclusive. But astronomers were able to get about 400 hours of time observing the TRAPPIST-1 system so far. And so when they were making the observations of E, they were looking at the light of the star, looking for the light of the star and the planet, and then trying to subtract out the light from the star to tell whether or not there's an atmosphere on the planet. But there's a problem that has sort of grown over time as people are starting to understand the magnitude of this issue, and that is stellar contamination, that the star is changing in brightness in its variability. And that when you've got the planets that are making their transits in front of this star, the star is also changing in brightness. And so how do you know that you're looking at changes in brightness because the planet is passing in front? And then how do you pick out which parts are the atmosphere and which are just the star changing its surface with sunspots and various activity? And so in a new paper, astronomers talk about the observations that they made with TRAPPIST-1e, and they give an idea that there are hints of an atmosphere, but it's not enough of a signal for them to make any kind of conclusive explanation. These data were picked up by James Webb back in 2023, and techniques have gotten better. And so I wouldn't be surprised if more observing runs, they'll start to get a better answer to this question. And there was another paper that came out that proposed a really interesting way that they could probably get better data. They suggested that you use the observations of B, which is known to be airless, and then compare that to the observations of E. So you'd watch a transit on TRAPPIST-1b, and then you would be able to see the variations, which include the contamination from the star as well as the effect of the planet. That would allow the astronomers to recognize the different patterns for how the star can contaminate the data. And then they could use that to better understand TRAPPIST-E. And they figure with about 15 transits of TRAPPIST-E, they would be able to get a much more comprehensive answer on whether or not there is an atmosphere there. So a lot of work is being done. We still don't have a conclusive answer yet. I'm sorry, but we will keep looking. Got a story about this from Evan Goff and Matt Williams on Universe Today. We talk a lot about what the US and Europe is doing for their space exploration plans, but China has a series of space science missions. And in fact, they have what are called their 5-year plans. And they're up to the 15th 5-year plan, which will be happening from 2026 to 2030. And they're planning to launch 4 missions during that period. And we got a recent video on Chinese television showing us all the different 4 missions. So the first one is called Hongmeng, and this is going to be a bunch of satellites that are going to be orbiting at the far side of the moon. And they're going to be a radio observatory that's going to be looking into the dark ages of the universe. And this is an observation that is being proposed by a bunch of different radio observatories. The aptly named dark ages of the universe are this time after the cosmic microwave background radiation was released, and as the entire universe cooled down again, but before the first stars and the first galaxies formed, the entire universe was dark, just giant clouds of molecular hydrogen. And the problem is that this wasn't giving off radiation that we would be able to observe. But there is this very specific radiation line that clouds of molecular hydrogen can give off, called the 21 centimeter line. Now, this is extremely redshifted early on in the universe, and so that's why you need a radio telescope to be able to see it. And you need one that is protected from the Earth's radio interference, which is why they're proposing the far side of the moon. And so this constellation of satellites would be observing this 21 centimeter line and try to map out the large scale structure of the universe during the cosmic dark ages. The next mission is called Quafu-2, and this is a sequel to the Quafu-1 mission, which is a solar telescope. This second mission would launch, and it would be studying the poles of the sun. And this is a region of the sun that is very poorly understood. ESA's solar orbiter mission has been raising its angle of observation of the sun, and we're getting sort of views higher and higher of its latitudes. And so this is the kind of observation that the Quafu-2 mission would make as well. And then there's a planet hunting mission called Earth 2.0. And this would work sort of in the same vein as the Kepler mission, as the TESS mission, the upcoming Plato mission from ESA. It would be monitoring thousands of stars, looking for Earth-sized worlds passing in front of their stars. And hopefully they'll be able to find an Earth-sized world orbiting within the habitable zone of a sun-like star. You know, and this is the holy grail. And that's why they're calling it Earth 2.0. Can we find another Earth? And then the last mission is the EXTP Space Observatory, the Enhanced X-ray Timing and Polarimetry Observatory. This is a mission that's going to be observing in X-rays and specifically looking in the environments around extreme astrophysical objects like black holes, neutron stars, and looking at how these interact with their environments. So those are the 4 missions that we can expect to see over the next 5 years from China. We've got a story about this from Matt Williams on Universe Today. If you're watching this before the weekend, you've got time to watch one of the best meteor showers of the year, and those are the Geminids. There are about 12 major meteor showers that happen every year. And, you know, my favorite is probably the Perseus, just because it happens in the summer in the northern hemisphere. And so I can be outside and it's warm and comfortable and watch the Perseus. You get about, say, 60 meteors per hour. But the Geminids are the most active. You can get about 150 meteors per hour when you've got good conditions. And this year we've got great conditions. And that really comes down to the moon, which is going to be about 25% waning crescent this year. It won't rise until about 3 a.m. So if you want to watch the Geminids meteor shower, you can watch them from anywhere on Earth. You want to go outside on December 13th and the 14th. So the night of the 13th leading into the 14th for you. And it really doesn't matter where you are. You just have to look to the sky and you should see a lot of meteors this year. And no moon polluting the skies. And one of the things that I really like about the Geminids meteor shower is that the meteors are actually coming in, hitting the Earth from the side. And so they're not going as fast as some of the other meteor showers where the meteors are hitting us face on. So they move a little more slowly. And so they create these big, long, lazy trails in the sky. So this is objectively the best meteor shower. It's just for us in the northern hemisphere, it's going to be a little cold. But for everyone else, should be fine. We've got a great story from David Dickinson giving you all the details on how to watch this shower. Every week we do a vote on our channel where you tell us what you thought was the best space news story of the week. And last week's winner was a landslide. And that was potential evidence of dark matter. So thank you everyone who voted last week. Now we're going to put this week's episode into the post tab here on our YouTube channel. So you can go there and vote. And of course, the best chance, subscribe to the channel. Click on the notifications bell, and then whenever you see our votes, vote, and that will train the algorithm. Astronomers have detected a blast coming from a supermassive black hole. It's about 135 million light years away in the galaxy NGC 3783. And in addition to this bright flash, astronomers also detected a gas ejection from this disk around the supermassive black hole. And this material is going about 60,000 kilometers per second, which is about 20% the speed of light. And what's really exciting about this discovery is that astronomers got this detection of the flash of radiation coming from this accretion disk around the black hole. And then they were able to watch as this jet of material was starting to emanate from this accretion disk. And what they found was that the process that happens in the disk around a supermassive black hole is actually surprisingly similar to the kinds of processes that we see on the sun. We think about the kinds of flares and coronal mass ejections that we can see coming off of the sun. And a supermassive black hole, something with millions of times the mass of the sun, can have flares and can have its version of coronal mass ejections, although at a vaster scale. And this flare didn't come from right at the event horizon of the black hole. Instead, it happened about 50 times the size, and we sort of measure the size of the event horizon and you map that out away from the center of the black hole, it came from a region out in the accretion disk around the black hole and then blasted out from there. And so what's great is that sort of solar physics and high energy physics are kind of the same, just at different scales. That supermassive black holes can behave like stars like our sun, just at a, ludicrous size. And I think it's really important here, like when I use the word they saw this and they can see this, they are detecting different kinds of radiation. They're detecting signals, different polarization, which is telling them about the magnetic fields. And so it's more like detective work, that they're able to look at the data that they've got and then be able to sort of reverse engineer what this must look like coming off of the accretion disk at the black hole, because it's so far away. It'd be amazing if we could actually see loops of material coming off of the accretion disk of this black hole. But, we'd need something much more powerful than the Event Horizon Telescope to even be able to do that. I've got a story about this from Evan Goff. On December 6th, NASA lost contact with its MAVEN spacecraft. This is the Mars Atmosphere and Volatile Evolution spacecraft, which has been in orbit around Mars since 2014. And it was sent there with the purpose of trying to figure out where Mars' atmosphere went. We know that early on in its history, Mars had a much thicker atmosphere, had a much wetter surface with liquid water on it, and then somehow through interactions with the sun and the solar wind, it lost its atmosphere, it lost its water, maybe into space, or maybe it absorbed it back into its interior. But the bottom line is that Mars is cold and dry today. So where did it go? And MAVEN did some incredible observations of the atmosphere and really are helping astronomers work out this puzzle of where the atmosphere went. So on December 6th, MAVEN was in contact with the Deep Space Network, which is what NASA uses to communicate with all of its spacecraft. The spacecraft went behind Mars, and then when it reappeared on the other side of Mars, it failed to reconnect, and NASA hasn't been able to regain contact with the MAVEN spacecraft. So they're going to keep trying, but maybe they've lost contact with it, and that's another mission that they can no longer communicate with. Now, in addition to observing the atmosphere of Mars, MAVEN was also serving as a relay for the various rovers that were down on the surface of Mars. So they may have to use a different relay or be able to communicate directly with Earth. Another James Webb story this week, and this is that astronomers have used Webb to observe the supernova aftermath of a star that exploded just 730 million years after the Big Bang. So about 5% of the universe's current age. And this object was originally discovered as a gamma ray burst. And it's the only way it could have been, because early on in the universe, only gamma ray bursts are bright enough to be seen. So astronomers detected this flash of gamma radiation coming from this gamma ray burst, and then they turned James Webb on this object and were able to detect the afterglow of what had occurred. And again, they're not actually watching the flash and watching the explosion. They're just detecting the presence of various chemicals in this area that's telling them that that's where a supernova went off. And so the gamma ray burst, these are thought to come from giant stars that collapse. And we see them across the universe at different times and stages. And then you get this sort of exploding supernova aftermath from when the gamma ray burst goes off. And so they used James Webb, they examined this region, and they looked at the chemical signature of what remained. And what they found was that it's actually very similar to the more modern supernova. And so this is a bit of a mystery area. We know that the earliest stars were less polluted by metal. And of course, the astronomer definition of metal, anything heavier than helium. And it was thought, well, so maybe stars exploding early on in the universe behave differently than the stars that are exploding today, the ones that are much more polluted with metal. And what they found in analyzing the afterglow from this supernova is that it's actually very similar, and that the sort of characteristics of how these stars explode is very similar to the way they do when they go off in a galaxy just, a few 100 million light years away from us. And they mapped the light curve and found that it followed a very similar level of brightness. But it really takes James Webb to be able to observe these objects because of just how redshifted they are. We've got a story about this from Evan Goff. on Universe Today. I hope you're enjoying this episode of Space Bites here on YouTube. Now, of course, YouTube has a few downsides for us as creators and for you as a watcher. One is that they put a lot of ads into their videos. And, we do what we can to minimize the amount of ads that you see. We don't put any mid-rolls, we don't put anything at the end, but we can't remove the ones at the beginning. YouTube forces those ads at the front of the video, and they make it really hard for us to be able to connect with our audience. And so we actually think that Patreon is a much better viewing experience for you. We're able to post our videos over there with no ads, and you're able to subscribe to our feed and get every single video that we do. So as a reward to get you to watch the version over on Patreon, we've got a version of this video, but with one additional story. And this week's additional story is trying to get at that question: why does Earth have plate tectonics while Venus doesn't? So I'm going to put a link in the show notes. You can go over there. You can just watch the video. You don't have to subscribe. You don't have to become a patron. You can just watch it over there. And speaking of stories, we've got just a handful of stories here on Space Bites. We don't have time to get through all of the stories that we're covering over on Universe Today. That's about 30 to 40 different stories every week, reported on by more than a dozen space journalists. And so if you want to get even more space news, see the full look, you should go and check out the Universe Today website. But I write a weekly email newsletter where I gather together all of the stories that we're covering on Universe Today. I write it all myself. There's no ads. It's completely free. You can get it. Go to universetoday.com/newsletter to sign up. All right, I'm going to talk about the search for atmospheres at the TRAPPIST-1 planets. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Barely Griffin, Brian Bodie, Caradon, Chuck Hawkins, Commander Bailock, Cy Nielsen, Darkfinger, Dave Veribioff, David Giltanan, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Porabach, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So talking about the search for atmospheres at the TRAPPIST-1 system reminds me about one of the greatest interviews that we've done here on the channel. That was with Dr. Megan Gialluca, who went through world by world of the TRAPPIST-1 system in incredible detail, telling us about sort of what are the challenges, the solar contamination problem, and what it's going to take for us to be able to make those observations. Now, the interview that I did with Megan was, I don't know, like a year ago. And so now we're sort of having the reality. There are more observations of the TRAPPIST-1d, which you can go and check out the stories about that. And now I've got the observations of the TRAPPIST-1e. And, Megan really called it, telling us how this is all going to play out. And, I really encourage you to go and watch that interview with Megan. It'll give you a lot of context to be able to sort of understand as we search for atmospheres in these worlds. And, we're starting to get through the habitable zone, and we're going to be out the other side of it again pretty soon. So hopefully somebody will find evidence of an atmosphere in the TRAPPIST-1 system. And if not TRAPPIST-1, then we will find evidence of an atmosphere around some planet around a red dwarf. Because, if we don't, if it just turns out that red dwarf planet after red dwarf planet is airless, then the current regime of space telescopes, James Webb, Hubble Space Telescope, are not going to be powerful enough to be able to examine the atmospheres of, say, Earth-sized worlds orbiting around sun-like stars. And we know that's possible. We live on one. And so we're going to have to wait for that next generation of giant space telescopes like the Habitable Worlds Observatory or the LIFE telescope or the extremely large telescope, which is being built right now in Chile. So hopefully we will find an atmosphere on a planet orbiting around a red dwarf star, and then we will get a much better sense. And maybe some of those will have the conditions for life. So stay tuned for that.